All right. Great. So thank you for having me. I'm here to talk about the retrofit manual, which is a living document. It was funded by the SNEP network. That is a program, a regional program at EPA Region 1 for south-facing Massachusetts and Rhode Island. So that's where the funding originated from. We partnered with VHB to develop the manual, and the idea was really to provide a resource for New England. And so New Hampshire is also a non-delegated state, so we also share virtually the same MS4 permit as the small MS4s. In Massachusetts, and we also have a nitrogen impairment that's we just got a EPA a new EPA permit for that's advancing what's being termed an adaptive management approach. So the idea of adaptive management is build and measure, adapt, build more, measure, adapt. So it's very different than the traditional TMDL process where you're locked into, however long a time frame and need to, achieve targeted reductions. The idea here is we're going to do our best to improve our management of stormwater and good housekeeping activities. And we're going to then monitor the receiving water. And in the interim, we've developed tracking and accounting metrics that can account for all the load reduction practices that we're implementing, both structural and non-structural. So the retrofit manual really fits into a scenario where a community or a watershed might be targeting load reductions, but not necessarily under a permit. So the retrofit manual really covers a niche area that it's not new development, it's not redevelopment, it doesn't replace those regulations and guidelines. What it does is it covers, I would say, opportunistic implementation measures. And because we're trying to kind of shoehorn in stormwater control measures, structural and non-structural as well, in the built environment, it really ushers in kind of a, do what you can, where you can, how you can kind of approach. And the science really is supporting that this can be effective. A lot of the background for this manual was developed in pilot projects that we had with different communities and other watershed associations, like the Mystic River Watershed Association. They're actively implementing small-scale controls, and they're getting funding to do so in the Mystic River. And it's something that maybe Neponset River Watershed Association might consider as well. There are funding opportunities that can allow the implementation of this type of approach and help communities meet their targeted load reductions. So that was a long introduction. I'm going to try to be quick and sort of informal. There are formalities here. Like, we did work with a great team, including VHB and EPA Region 1. Mark Voorhees really spearheaded this. He's since retired, and I kind of called this the Mark Voorhees Memorial Manual. What it really does is it codifies a lot of the metrics and measures that are in the MS4 permit already, particularly Appendix H. In Appendix H, there's performance curves in there that we basically co-opted and developed into a design tool. And you'll see that reflected throughout the manual. We also included all new representatives from all New England states, or we didn't have representation from Maine, but we tried to get representation from all New England states. as we expect this to be sort of a regionalized approach. So I'm just going to skip through some of the formalities here. The goal here is really to help and really assist communities who are faced with growing implementation challenges and growing regulatory requirements to reduce particularly nutrient loads to receiving waters, and to kind of usher in or help assist with ushering in a new kind of era of implementation. I sort of feel like we're in a transition point where we're moving from what has been kind of a planning type of economy into where we develop phosphorus control plans, or we develop nutrient control plans. We develop plans that give ourselves timelines and set us on some type of track to achieve a targeted load reduction. And we're moving into this implementation, I guess, type of economy where we're going to be actively implementing over the next decade or two. And we really need to, what the retrofit manual really serves as, it's sort of a feedback mechanism. So we really took over 2 decades of research and science-based findings, and we tried to, as best as we could, develop those into guidelines to assist communities. So I guess more simply, I could say it was an attempt to make the rules around implementation a little bit more flexible. And I think I'll show you more what I mean by examples and anecdotes as we go through. So this is really meant to be a tool in the toolbox to help municipalities with these growing regulatory challenges to basically begin to design and implement stormwater control measures that they can kind of adopt as a sort of a new state of the art practice. So this manual has been developed. It's downloadable from our website at the University of Hampshire, or the snetnetwork.org. It's on their website as well. So I encourage you, if you have lingering questions, the manual really covers everything that I'm talking about in much greater detail. So I want to just talk a little bit about this kind of trajectory that we're on here. I was just in a meeting. There's a lot of infrastructure dollars coming out, infrastructure dollars to assist with disadvantaged communities. And, so EPA is really interested in helping. And so I was in this meeting where EPA is leveraging some dollars for EJ communities, 2 in particular. I won't name the names to protect the innocent, but the original communication was, we have severe flooding problems. And they were really looking for a solution to their flooding problems. I think stormwater is kind of an emerging field. And because it's emerging, we've learned so much in the last decade, and what we're doing now is so different than what we've been doing traditionally, that you really have to be on your toes to kind of stay ahead of the game. It's very common, especially in the water utilities, like drinking water and wastewater, to have a problem and hire an engineering firm to solve the problem. So at a place-based utility, like a wastewater treatment plant, you can do that very easily. We need to reduce our nitrogen to 3 milligrams per liter, or our phosphorus levels in our wastewater treatment plant. And so you link up a unit operation or a unit process that achieves that goal. In stormwater, it's very different. Our problems are prolific. Our problems are exacerbated by not just climate change and changing weather patterns, but also by the continuity of development. And so I think there tends to be this idea that, with one fell swoop, a shot of a strategically aimed silver bullet, we can solve these problems. And I have to say that I don't think that is really the case. This is really a behavior change, and and stormwater is very much a, I guess it's a list of strategies of good housekeeping, right? How to keep your closed drainage network working properly and as clean as possible. So it's really, so this is a Gartner hype cycle, and I've shown this a lot just because it mirrors kind of my career, where you have this peak of inflated expectations, and I would describe it as, bioretention is going to save the world. There's places still where people are trying to, implement bioretention systems to stop and abate climate change. And, this is not going to happen. This green infrastructure or these stormwater control measures are a toolbox, and they can help, but they can't do it all. And there's really no silver bullet. So, we fall into this trough of disillusionment where, our bioretention or our green infrastructure demonstration projects are not going to save the world. And now we're slowly kind of trying to climb out of that. And the slope of enlightenment is really the nexus of what the retrofit manual tries to usher in. It's how do we manage our infrastructure with the tools that we have, and with the aim of making things a little bit better with every advancing year, with every project that happens in the municipality. How do we incorporate better stormwater management? And so I would think this is the tale more of, 1,000 drops of water, or 1,000 drops of water eventually make a mighty ocean, and it's less of, a one-shot. We're gonna solve stormwater overnight. So the way I kind of put it is, in a lot of sense, in the planning economy, we devise a schedule, we devise a load reduction, and it's sort of a finish line approach. A finish line approach means we have the plan, and all we have to do is implement it, and then we're going to have attainment in our water bodies. I just don't see stormwater really evolving like that, just because we're continually learning. Every system that we put in, we learn more, and we have this culture of operation and maintenance of these facilities. There are some systems that the communities just simply do not have the infrastructure or the staff to maintain. So why would we implement those types of technologies that then can't be maintained? Something, for instance, that comes to mind is something like porous asphalt. There was a lot of, or permeable pavements. There's a lot of really allure in the beginning about permeable pavements, and they're pretty phenomenal at what they can do and the changes they can impart on the hydrology, local hydrology. However, unmaintained, they fail. And so we've seen a lack of the ability to maintain these systems. And then what happens is, over time, unmaintained systems basically revert back to as if you had done nothing. So taking a more starting line approach means that we can include this feedback cycle, and we can include the iterative adaptation that happens as we implement. So we've done this. I think that the area that probably hits closest to your home is we're doing this in the Mystic. Arlington really took advantage of a small scale control, like infiltration trench, and Wayne Chenard, the city engineer there, has been implementing. We started with 9 systems, and I think he's probably over 100 by now. Small scale controls being implemented throughout the environment. And again, I think I would recommend that you reach out to the Mystic River Watershed Association. There could be some synergies there. in discussing kind of strategies and how to harness technical support and as technical assistance as well as financial assistance. There's a lot of help out there right now. So what we talk about in the retrofit manual is a planning approach for sure. You know, this is something that VHB helped us with this manual. They do a lot of work with Mass DOT. They do a lot of work with Rhode Island DOT. And these are massive planning efforts. You know, DOT doesn't do anything. I mean, they're working on a 5-year time frame, meaning the planning that they're doing now, the implementation is going to happen in 5 years. The other strategy we really kind of discussed is sort of an, I guess, an opportunistic approach. So anytime you're updating infrastructure is a good opportunity to implement stormwater controls. And we use these performance curves. So some of you might recognize this. This is right out of Appendix F of the MS4 permit. It's basically a performance curve that shows load reduction associated with a physical storage capacity. So every system has a physical storage capacity, and that's related to the performance. And it's really the first time, typically we talk about a 1-inch physical storage capacity or a 1-inch water quality volume. And this really allows us to take credit for systems even down to tenths of inches. Sorry about that. So we describe this and the design strategy behind it. In the manual, and I guess I would welcome you to visit that if you need more description or more details about, you know, this design strategy. It's based in science, so a lot of the original ideas behind the performance curves were, you know, if we can't fit a conventionally sized system, what is the benefit of doing what we can? And so that was the original sort of focus. And we did, we got funding to study a couple of systems and really validate the curves that were developed. And we looked at a bioretention system and a subsurface gravel wetland system. And the designs of these systems were just fit into the environment. So oftentimes in a retrofit scenario, you don't have the ability to take all the space you want or think you might need. In this particular instance, on the right here was a linear gravel wetland. And you can see we're stuck in between. This is a drainage right-of-way. The river is really the discharge point, but we're stuck in between two private property owners. And what we have is the drainage easement. So the right-of-way that the municipality owns and maintains. And that was really the only spot that we had to fit this. So it was stuck into the already built environment, and it was sized based on what the area could accommodate. Same thing with this median strip retrofit. The commercial property owner here wanted nothing to do with sacrificing parking for stormwater control. So we were forced to confine the system within the median strip, within the real estate that we had accessible. So both these were not designed in a real strategic way. They were just fit. And so we can calculate that the percent of the normal sizing that we would have done conventionally, and the subsurface gravel wetland was 1/10 of the size that we would normally size at had we been designing this from the start, and the bioretention system was about 20% of the normal size. So dramatically, I guess what we call undersized. So we studied these systems and the performance for the 1/10, 10% design. All the rainfall was outside of the design storm. So every storm we monitored was outside of its design depth. right? And this is our conventional sort of approach to how we design systems. For the 20% system, most of it was outside of the design depth. There was only 35% of the storms that were within that 0.2 inch rainfall depth. But when we look at the data, it tells a very, very different story. So you can see here, this is just the average of 4 different bioretention systems, and the green is the undersized system. And while we were only 20% of the actual design, we didn't get 20% of the performance. We got about 90% of the performance. So the penalty for undersizing systems from a water quality perspective isn't as great as we would have thought. And so this really ushers in the approach where we do what we can, where we can, how we can, and we get attendant benefits, from the urban restoration approach. We're really getting the water quality that we need without sizing what we thought we needed. And we can see the same thing. That's sediment, nitrogen, phosphorus. Really, the story is the same across the board. And when we compare the measured results to the modeled results, the performance curve results, we really have validated that those performance curves are really doing a good job of depicting what is actually happening in the field, where our models oftentimes are not. And I could go on in that, but for the sake of time, I'll just sort of end with an example of work that we're doing. But through the SNEP network, we have a training program, and North Kingston is going through a design charrette where we're meeting and we're discussing retrofit opportunities and we're discussing approaches. And they're actually designing these using these tools that are embodied in the retrofit manual. So for North Kingston, they have this coastal area, a large medium density residential development discharging right to the ocean. And then they have a municipal parking lot that they want to redo. So the focus here is on this drain line that's draining this 2.71 acre watershed. How can we kind of fit in a treatment system to help reduce nitrogen in this area? And in the parking lot, it's a little less than an acre. And again, how can we treat the sheet flow from this parking lot after it gets rebuilt? And so what we're considering is, so if you look at the conventional approach and we were going to size this, it would require, conventionally, it would require about 11,000 square feet of area. And it's just simply too much, right? There's not the budget, there's not the budget for that. And there's really not the space. This is a recreational space that's used year round. And so this is where we're employing the tools embodied in the retrofit manual to identify what we can do. And there's ways to optimize this. So if you look at the curves, we do a knee of the curve kind of assessment. And if you're treating about the 0.4 inch rainfall event, it's anywhere from 0.3 to 0.6, depending on the pollutant of concern. If you're treating that range, you're really optimizing performance. And what we'd say is beyond that inflection point, you're getting diminishing returns for it. Larger and larger expenses. So we have to shrink it down. What we're considering is a bioretention cell to treat the sheet flow off the parking lot, and only a 1,500, so a tenth of the size system to treat this drainage area. And if we trust the science tells us that we're not going to get 10% of the benefits. We're going to get almost the exact same benefit with maybe a slight penalty. So this is a very cost-effective way of meeting some of our water quality challenges and working within the built environment to get something better. So we really operate at what I'm calling, it's the hydrologic Hippocratic Oath, right? We're not making it worse. We're just trying to make it better. So we're not taking away capacity, we're adding capacity, and we're just not getting too stressed out about not having the sizing convention that we would typically have employed, and really trusting what the science is telling us about these small scale controls and the big benefits that they actually impart. So I think I'm going to stop there. I could certainly go on. I think if you want more, you know, I can come back and I can talk about some of the other elements, but I think I'll stop there and we'll take questions.